So the NR stands for New Radio 5G Air Interface. So in the first half of the talk, we will be discussing the NR objectives, its features, different signaling, access and control procedures defined as per the 3GPP standards and their timelines. And in the second half of the talk, we will see detailed deployment scenarios at the Art Garage. And Art Garage Incubatory is a state-of-the-art manufacturing and testing facility for robotics and autonomous systems. And this facility is associated with ARTPARK. Center for Excellence in Wired and Wireless Technologies is located at Art Garage, and it provides and strives to provide 5G communication infrastructure for the startups to test and evaluate their solutions. And I welcome all of you. So let's move on to the new radio objectives. So the objectives are high data rates, low latency, high connection density, and spectrum efficiency. So as we wonder why NR, right? So as the number of IoT devices increases every year, the existing generation of radios are not capable to provide coverage and handle capacity. So and also over the time we need several new services. So in that perspective, we can summarize that at very high level, that the new radio should be able to provide us high data rates, and then for enhanced mobile broadband, and low latency for remote surgery and remote uh, control operations, and also for the high density of nodes in the event of mega gatherings at the stadium. So in order to achieve each of these performance objectives, we will look at the 3GPP NR features. And before diving into the NR fundamentals, we will look at 3GPP standardization efforts and its roadmap for 5G to 6G. So 3GPP is a group of telecommunication organization that works together to create cellular technology standards. So 3GPP is also responsible for defining technical specifications and requirements for cellular technologies. So it organizes its work into three streams. One is radio access networks, the other is service and system aspects, and core network and terminals. So there are three streams in which work groups are organized. And the timeline for 3GPP is shown here between 2018 to 2030. Here, what do we mean by 3GPP? I mean, it is described as third generation partnership project. And you can see that 3GPP 5G shows release 16, release 17. And what do we mean by release, right? So release refers to the version of technical specifications that define a particular set of features and capabilities for a mobile network. And each release is typically associated with specific milestones in the development of network technology. So release numbering is used to indicate the progression and updates in the development of mobile networks. And it is also associated with a specific timeline and a set of deliverables. So right now, the products of 5G are out, and 5G is evolving with several new use case scenarios. Simultaneously, study for 6G and specifications for 6G are expected to come out around 2028. So eventually the 6G products will be coming around 2030. So these standards ensures interoperability between multiple vendors and mobile operators. So 3GPP also defines two different 5G architectures or two different NR radios. One is standalone and the other is non-standalone mode. So in the standalone mode is nothing but it is fully independent uh, 5G architecture, where it is seen in the left hand side of the figure, where the 5G radio network connects directly to the 5G core network. And this SA deployment can be used for advanced use cases such as ultra reliable low latency. Non-standalone mode uses 5G radio access network in combination with the 4G LTE infrastructure for data and control. So this allows operators to quickly deploy 5G by leveraging the existing 4G infrastructure. So the 3GPP started working towards standardizing, self-optimizing and self-organizing network use cases for 3G and 4G networks, starting from release 8 up to release 12. So the specific standards are described in detail in network automation and management features. So the left-hand side figure shows the phases in a self-organizing network. So the snapshot phase will identify the cells with bad key performance indicators values. And the next phase is the action phase, where they perform where that phase performs automatic parameter changes. Then in the feedback phase, the key performance indicator of the same cell will be collected and check whether it has been improved or not. If there is no improvement, the configuration parameters are reverted to the old settings. So these are the different phases in self-organization networks. In general, self-organization networks automatically adapts to instantaneous traffic conditions, and it maintains high quality user experiences. How it does that? You can look at the right hand side figure. So earlier the configuration was deployed manually, that radio and core network parameters were done manually, and the radio optimization engineers and using some tools they used to configure, optimize and heal the network. But using these self-organization network applications, these configurations are automatically deployed, and it is known as self-configuration, self-optimization and self-healing. And if you look at what are the functionality under each category, the self-configuration takes care of the automatic radio parameter settings, such as power levels, frequency settings, antenna configurations, and so on. And in the network element discovery, it can automatically detect and integrate each user equipment can automatically detect and integrate themselves into the network, allowing for rapid deployment in large networks. So, and also the automatic assignment of IP addresses and backhaul resources are possible in the self configuration. In the self optimization, you can see that dynamic control is possible, power control is possible in real time, so that the energy efficiency can be achieved, and load balancing can be performed. Like for example, we in the last class unit we saw that the femto cells and pico cells are there. So instead of one single base station, we were using, 3GPP has specified several usage of several femto and pico cells to reduce the energy consumption. So we will also do load balancing among these cells. So automatically redistributing the traffic across different cells and different frequency bands to avoid congestion is done by the load balancing unit. And also the interference management, like dynamic optimization of resources to reduce the interference. Everything is taken care there. And in self healing, fault detection is done. Under fault detection, radio link failures can be identified. Then hardware failures or software issues, right? So I remember somebody from the last talk asked, how would you identify a beam failure? Particular beam has, if there is a failure, how will you find out? So the self-organization network, with the help of AIML and other things, they can identify the radio link failures and correct it. Automatic recovery happens. So the network can take corrective actions such as rerouting, reconfiguring the parameters, or bringing up a backup equipment to restore the services, and so on. And also the performance monitoring can be done. So if you look at this organizing networks, when compared to the conventional radio access network optimization process, um, with the SON, we can see that conventional RAN takes 8 weeks, and compared to SON takes only 8 hours. So if we see the split up of the time, collecting data from the drive test, existing configurations, and corresponding KPIs, everything has to be studied. Like the periodicity of customer complaints, everything has to be collected, and this collection takes up to 2 weeks. And then performing network optimization, reconfiguration, and after reconfiguration, analyzing the KPI, that takes about 3 weeks. Then next is the monitoring phase. Okay, we have reconfigured and optimized. How is that network performing? So monitoring that takes 3 weeks. So totally 8 weeks to do this, right? So, and it also involves very high operating cost. Whereas in the self-organization network, it takes only 8 hours, and also with very low operating expenditure. And that is why the industry is moving towards self-organization networks. So the application of self-organization networks is like automatic neighbor relation, or like a coverage and capacity optimization. So this coverage and capacity optimization is really needed in the large gatherings, like mega events, like stadium and concert events, right? So some kind of self-organization network is needed to implement such scenario. And the radio resource management is also a key component of self-organization network, which handles tasks like handover optimization, interference management, cell planning, load balancing, etc. So several, this machine learning and artificial intelligence um, uh, based predictive analytics and optimization, anomaly detection is very extensively used, and this allows the network to learn from the past behavior and optimize for future scenarios. So anticipating the problems before they occur and dynamically adjust the network accordingly. So this is where the standardization activities are moving. And what does the 3GPP says? We can look at this figure. We can see that the AI and ML standard activities in 3GPP. So as I mentioned, SA stands for services and system aspects. So the working group 2 and 5 are expected to complete around 2026, and the radio access network groups 1, 2, 3, and 4 would deliver their specifications by 2026. And 3GPP states that from day one of 6G deployments, AI and ML standards will be in place. So, if you look at the use cases of AI or ML for NR air interface, it is useful in beam management, positioning, channel state information, mobility. So, they are taken up by the 3GPP standardization activities. Yeah. So release 17 studied and identified the most important use cases for AI/ML based optimizations. And release 18, 19 brought the corresponding progression in technical specifications. And you might notice that release 19 is focusing on coverage and capacity optimization, network slicing, mobility optimization, right? So although a few other things. And enhanced network automation is fast evolving since release 15, and technical specifications were released in several phases through phase 1 to phase 4 in the form of release 16, 17, 18, and 19. Is there any questions at this point?
There is a standalone and non-standalone, correct? And when you
Right,
said it supports ultra low latency, and you said non-standalone, it's used for quick deployment. So does it mean that in non-standalone, you may not get ultra reliable low latency features?
So I would say that the latency compared with 5G and the 4G, right? Like when compared to 4G, 5G will have much lower latency. The reason is that we would have seen in the last unit that it has flexible numerologies, right? So because of that, it is able to schedule users with much lower latency, and because of that, you will have better very low latency. The moment you bring 4G architecture also, then the numerologies are fixed. Then accordingly, there is you have to wait at least for 1 millisecond before your next user is being scheduled, right? So that is what we learned from the last this one. So we can also see in the further slides. I will bring it up again.
Madam, you're showing that release for 19, 18 and all.
Right,
So as
right.
19, as per release 19, are there
Okay.
any specific scope or challenges for NB-IoT?
NB-IoT. Okay.
Release 19.
Yeah, I would say that channel state information will always be needed in all communications. So NB-IoT is also one of such things, and also mobility, right? Let's say this NB-IoT node has higher mobility.
It is
Then
for static.
release.
It is for
Yeah.
static devices. NB-IoT.
Okay. Okay.
Not
So
mobility.
then
Not
I think like I have to look it up. So channel state information might be definitely be useful. Yeah.
it is
I mean,
scope for
you can also share your experience. Like, have you looked up any NB-IoT? So which release are you working on currently?
I'm seeing release 14, 13 and 14, madam. But
Okay.
19
Okay.
is not yet looked into. But that's what I am asking, whether there's any support or scope for release 19 to change the.
Okay, okay. So we in our lab we are using 15 and 16, and yeah, we'll let you know. Like, yeah. Okay, now we'll look at the NR features that realizes very important NR features that are um, new to 5G, right? So, as I mentioned, this flexible OFDM numerologies are very helpful in achieving the different carrier aggregation methodologies and also achieving higher bandwidths, right? Like um, similarly, I was talking about the slot duration, right? Like in 4G, you have to wait at least for 1 millisecond, so that then you can fine. So you can also schedule a user by 62.5 microseconds with the help of using the numerology 240 kilohertz and so on. Hence, the scheduling latency is reduced because of this flexible numerologies. So apart from flexible OFDM numerologies, the time division duplexing configurations allows flexible symbol slots. So as I mentioned, these flexible slots can be dynamically changed into downlink or uplink, and the cell and the device will negotiate before its session starts, so that the device can achieve use a um, best configuration which is suited for its device environment and its application, right? um, Regarding carrier aggregation, 5G allows the aggregation of interband. Interband is nothing but aggregating channels from different frequency bands. So, in this case, the frequency bands FR1 and FR2 can also be aggregated. Channel aggregation can be done. And intra band is nothing but aggregating different channels within the same frequency band, right? So with the FR2, you can achieve up to 400 megahertz of bandwidth, and with FR1, the maximum that you can achieve is 100 megahertz. So FR1 is sub gigahertz, and FR2 is the millimeter wave band, and it's around 28 gigahertz and up to 52 gigahertz and so on.
ಬದರಾದರ ಏನ್ ಬದರ
Right. So in release 16, they also allowed further progression with dual band operation, and you can see that bandwidth part is a new feature in 5G. According to 3GPP specification, UE channel bandwidth is up to 100 megahertz for a sub gigahertz, right? As we saw, and 400 megahertz for the 6 gigahertz band, about 6 gigahertz band. So, which is much wider than the bandwidth of the 4G, which was around 20 megahertz. So most of the time, the users will not be needing that much. They won't need that much high data rate provided by the NR bandwidths. So NR defines the new concept that is called bandwidth part. So UE can operate in the narrow bandwidth, and when the user demands more data, then the GNodeB will allocate wider bandwidth. So this makes NR an efficient solution despite the support of the wide band operation. So in general, UE can be configured with 4 types of bandwidth paths, like for downlink and uplink. But at a given point of time, only one bandwidth path is active for downlink and one for uplink. So bandwidth part is nothing but a contiguous set of resource blocks on a given carrier. So whenever GNodeB configures a bandwidth part, it includes informations like bandwidth numerology or bandwidth frequency location, right? All such details will be given. The bandwidth part is configured for each UE according to its UE capability. So hence multiple UEs have different bandwidth capabilities and can be served in a single wideband NR carrier. So NR does not support carrier aggregation within the LTE, and thus dual connectivity is needed to support the aggregation of LTE and NR throughput. In the sense that, so only NR supports the carrier aggregation. So next we'll move on to NR access and control procedures. So we will look at the random access procedures and signaling such as radio resource control and non-access stratum signaling. So random access procedure has 4 steps. One is the random access preamble transmit, that comes from the UE. And then for that, the response will be the GNode will give a random access response message. Once that is received, the RRC connection request will come from UE. Okay, so then RRC, we can look at the picture and then right. So after receiving the random access response, we'll also have to look at so the random access response will contain message like UE identity and then the connection request parameters. That is nothing but what service type does the UE wants, and then the GNodeB will process the message and it will prepare the RRC connection accordingly. So this is shows the NAS signaling, non-access stratum signaling, for a registration accept case. So under the registration accept case, you will see that UE will send the registration request over N2 interface to the access mobility function. So after receiving the registration request, AMF will start a timer, and then both UE and AMF will perform their side of authentication and security procedures individually, right? Once they have done, after successful authentication and security procedure from AMF, it will send the registration accept message. And once it is sending this, it will stop one of the timers and start another timer. So once UE receives this registration accept, it will check all the parameters which are assigned for it, and if it is okay with it, then it will send back registration complete, and then the AMF stops its timer. The second case is that the registration has been rejected. So if we look at it, similarly, there can be, like, even after this authentication process and security, everything has been successful, this can come. This registration reject is possible, and AMF will give a valid cause, like what is the reason why I am rejecting, right? So we'll see what are the different types of causes, why this access and mobility function can reject a call or reject a UE. So one of the causes is that illegal UE, means that when the network will be refuses the service to UE either because an identity of UE is not acceptable to the network, or because UE does not pass the authentication check. Okay. So, and then the other one is like illegal ME. It means that the network has blacklisted the UE. Likewise, you can see that tracking area not allowed, and roaming not allowed in this tracking area. So, authentication and security can pass, but as per the subscription, they have not subscribed for roaming. So then roaming not allowed in this tracking area can be the cause. So AMF gives the reason for the rejection. And there's also this new cause, number 72, which says that non 3GPP access to the 5G core network is not allowed, right? So this is like uh, I mean, if you have not subscribed for non 3GPP access, then this kind of reject can happen. And if you want to know more about the different type of causes, then you can look at this technical specification at 24.501 5G. So at this point, is there any questions, or we can okay, so then we can move on to the next this 5G network deployment at CoE WWT Art Garage, right? So we will be discussing each of the test beds in detail in the upcoming slides. So before moving on to it, I'm just refreshing our knowledge on cloud radio access network. So in 5G has three components, major components like 5G core, GNodeB, and user equipment, right? So, and the GNodeB can be further disintegrated or a distributed manner in terms of centralized unit, distributed unit, and radio unit. And the link between distributed unit to radio unit is the front hall, and the CU to DU is the mid hall, and between the core to CU is the back hall. And these communication links can be either optical, or it could be millimeter, or it could be cellular links based on the distance and the requirement. So if you look at this figure, this broadly describes the architecture available in CoE WWT. In order to realize the private 5G network, we have several combinations of CU, DU, and RU with core and radios from different vendors. So in this figure, we can see different open source core such as OAI. I was trying to use my pointer. Okay. So in order to realize private 5G network, we are using this open source core networks such as OAI, SD core, and then Open 5GS in the left hand side, right? And there's a box, and then the we also use third party commercially off the shelf core networks such as Neeral, Proyava, and other networks. And also the core is connected to the network with the commercial radio. I mean, the core is also we we will be able to generate and simulate the traffic load in the core. Um, the, we use commercial radio units with 90 and 120-degree antennas with better coverage for the whole area in the art garage. And that can be, you can see that when you visit on March 13 and 14. You can look at this red dotted box, which shows the non-real-time radio interface controller and near real-time radio interface controller. Um, right? So that basically is a very key ingredient or component which helps us to acquire like real-time channel state information and the physical layer parameters, which you can use it for the self-organization networks that we were discussing in the previous slides, right? So if we can access from this CUDU, can directly from the radio unit, if and the from the GNodeB will be directly connected to these radio interface controllers, can collect information and run uh, AI applications, AI ML applications on the collected data, right? So, and then the GNodeB and UE simulators are also supported in the open air interface. Like even if you don't have a physical equipments, the open air interface provides the simulator to test all the functionalities. And apart from that, we have monolithic GNodeBs uh, like all CUDU and RU is in a single box. So we have examples for monolithic GNodeBs. So when you visit, we can see it in person, what I mean by that, and also through our upcoming videos that I'm going to show in the further slides. So, as I said, there are three different components like core network. So, in the core network, we have Neural, Open5GS, OAI, Proyava, and then the UE, we have this 5G dongles from the Quectel Qualcomm modules, right? And then the UE, the commercial UEs, and then the open source radios like X310, B2, 10, etc. are there in the lab. And we also have radios like radio from the commercially off-the-shelf radios like Signaltron, Resonance, and then the USRP X310 along with OAI interface is used as the GNodeB. So the other two are the monolithic GNodeBs. So using all these components, we have developed four different types of test beds. So if you look at um, the first one, um, you have Open5GS core in the Open5GS core is used in one of the server, and in the second server we have used the OAI radio access network combined with the open source X310 radio, and it is operating in N78 band. Mm, and we connect these 5G dongles and commercially off-the-shelf UEs, and we could connect to the network and do evaluation, performance analysis, and all. And the second test bed is spread around the entire art garage facility, which is around 75,000 square feet. with three different GNodeBs located quite far apart, and then each one of them are connected to the core via optical cabling. And we have we are testing with drones, integrated with 5G enabled drones are operated in this network. And we also have the commercial UEs. Um, we can go up to around 600 to 1 Gbps downlink rate, and then about 80 to 100 downlink, I mean uplink rate. Right. So if anyone wants to use the facility for their own evaluation, you're welcome to come and test here. And the third 5G testbed is we have this neural core network, and then the um, um and their mobile edge computing server is connected with the resonance radio. And so more or less we have tested with N78 band, and with all 5G dongles and POTS UE. The main contributor we also have highlight is that the testbed 4 is provided by Bharat 5G. This is one of the 100 labs set up all over India in collaboration with the Department of Telecommunications. So we have one such setup here, and we will see the demo video in further slides. Here, neural core, yeah, right. So yeah, Signaltron and neural core are the combination used here. So now we can look at the video in. So you can see that it is connected to a private 5G network called Art Garage. I don't know whether you saw that. Yeah, ARTG 5G is the private 5G network that we are using. And here the drone is having a 5G, it is 5G enabled, and it has a SIM card, and it acts as a UE connected to the same. So any UE that is connected to the same 5G network will be able to get the video transmitted by the UE. So that is what you are looking at in the yeah, in the second one, broadcast is seen in 5G compliant mobile unit. That is what you're seeing. And the latency is very low. And this rebroadcast latency is very lesser when compared to Wi-Fi. And we saw Shreya demonstrated from Vedan startup in Art Garage. You can meet uh, each one of them during your visit. And next is the in this video we show the Open5Gs initialization, where we first start the Open5Gs script, which runs all the network functions like access mobility function, session management function, authentication server function, and all the network functions are initialized. And once it is started, we can run the IP routing commands, And you can also check the status of the command, which will indicate which network functions are active and which are not, right? If there are errors in the configuration files, also will be indicated, saying that some of them are active and some of them are activating, like in the process of activating. Then the um, your core network is not in a position to be used with the GNodeB, right? So you have to debug what is the root cause and everything. Okay, so we will move on to the next video, where this USRP based uh, 5G testbed will be connected to the UE. So here we will see that an open source radio is used as a GNodeB, and commercially off-the-shelf UE like a mobile is used. First, we are starting the open air interface GNodeB. In the USRP X310 is the SDR used here. Once it is started, this GNodeB is continuously sending the master information block in the MAC frame slot. That is what you are currently seeing. So when it switches on, it initiates the random access procedure. And then if the UE checks, gets back the random access response, and if UE checks that its random access rapid ID is matching, then it will extract all the essential information from the master information block. Now the UE is getting restarted and it is getting connected. So in the screen, you are seeing that, yeah. So in the screen, the network name is shown as WWT ARTG. So that is another private network in the Art Garage, right? So it is WWT 5G. Stands for Wired and Wireless Networks, Center for Excellence. And now you can see all the random access response messages. So this display here, it during this display, we can see that signal to noise ratio, block error rate, and then the modulation coding schemes are seen, which are exchanged between the UE and the GNodeB. Next, we will be seeing the Bharat 5G lab setup. So as I said, it is the setup sponsored by Government of India in collaboration with the um, um, yeah. So once the so the here you can see the speed test is being carried out, and then the video streaming is happening, right? And then you can see that the core and the radio, I mean the one with the antennas here in the second rack is the GNodeB, and the core and the MEC servers are placed below that. And we have the router which sends the signals from the GNodeB to the outside. With much higher good radio access network is provided in this um, router using this router. And then you also saw that this was demonstrated by our team member, CoE WWT member Sanjay Shukla, who did the video streaming and 5G demonstration. So you can personally interact when you're during the demo sessions on March 13 and 14. Yeah. And you can see that yeah, one thing I forgot to mention, that how many radio units and how many um, um, the dashboard will be showing the number of cores, radios, and UEs connected. Right, so that is also GUIs are provided, and we can do the testing. So yeah, that's I think we are ahead of the schedule, but I'm open for the questions now.